G'day mate, Mac, your Quantum Odyssey tour guide, and I have a very special announcement regarding an upcoming update expected this weekend. I had in contact directly with Lore regarding my findings while struggling with the last node, which is a classical computation challenge, in my last live stream while rearranging the master and target gates of a multi-qubit gate, which is for representing a classical computation gate, namely XOR, an AND, an OR, or a NAND. Regarding the future live streams, the Ring 3 live streams will be conducted on Canada Day and Independence Day at 6 a.m. Eastern Daylight Time or 12 noon at Central Eastern Summer Time. Regarding this special live stream, there are 3 items I have to go through. All 3 of these items will be relevant to this bug report. The introductory diagram that I've posted is a demonstration, a circuit diagram of a multi-qubit gate that has been permuted. In this case, the second and the first qubit in place order value is used as the input to determine whether the ground qubit is to be flipped. So this is an XOR. Now we use the answer for the output, that means whether the XOR of the first 2 inputs holds, and then the first qubit input, again applying an AND to flip the second qubit if the answer, the first answer, and the second input is set to true. So these are the, let's go with the forge diagram. So we have this. So this is the XOR using the first and the second, and then there is the AND, which uses the ground, which is the answer, and the first. So ground, so 1, ground, and first, so 0, 0, 0, 1, and if both of them are true after the XOR, we transfer this sigil from the left half to the right half. So only if both the ground and the first qubit are 0 do you switch the lanes from the left half to the right half, and vice versa. So let's go with the diagram there. So 0, 0, 0. So 0, 0, 0, 0, 0, 1. So 0, 0, 0, 1, 0. Because the XOR holds, it's 0, 1, 1. So 0, 1, 0, 0, 1, 0 goes all the way to the very right. 0, 1, 1. So now let's go with 1, 0, 0, 1, 0, 1. Then we have 1, 1, 0, so no switch. Finally, we have the 1, 1, 1. 1, 1, 1 would have to switch lanes only on the second layer because the first and the ground qubit is at 1. So here is a demonstration of permutation in action. So this combination of controlled x's, so 0, 1 0 over there. So now let's express this in decimal. So we have this 0, 1, 2, 3, 4, 5, 6, 7. These are all the input-output combinations. The expressing a classical gate in quantum gates is like flipping the output qubit. So when the output qubit is flipped, that means the classical gate evaluates to true. So now we flip this, so 0, 1, then we have 3, so 3, this one's flipped. Then we have 4, then we have okay, 0, 1, 0, 1, then 2 is all the way to the right, then 3, so 4, 5, now has to switch places. Then 7 goes to the slot of 3, 7. So 4 is 1, 0, 0, 5, and 6. So in total, there are 5 lanes that has to switch positions in this gate. But ultimately, this is a permutation matrix. But this is our update. Just to express this one more time. The reversible classical gates are 3-qubit gates that are non-symmetric as a whole, but symmetric between the two input qubits. This leads to some confusion between rearranging the master or the targets. So custom gate the master, then the 2 qubits, the 2 targets. And this is the demonstration of XOR, the rearrangement of XOR, which the index on the right is the place value of the qubit that is used at the output. So the familiar XOR uses the ground qubit as the output, while the first 2 as the inputs. The master qubit is placed on qubit number 2. So anything else is the target qubit, which it says master and then the number of the slot which the master occupies. This one also on the circuit editor is also question mark master master. So it could represent this gate or this gate. So they're no longer the same gate, but they're represented in the same way. This leads to the confusion. The last example, which groups the pairs in the left and the right, performs crisscrosses only if it's in the middle 2 per each half of the whole forge. This is when the second qubit is the output. So you cross from the left half to the right half and vice versa. Here, we know that number 2 is always the one that serves as master, but we now permuted the master to the ground slot, so the question mark belongs to the right now. Okay. And then we have 0 and 1, which we will have master and master. The important thing is the question mark or the master qubit is actually an input. This is where the asymmetry lies into play. It should represent the output to make it symmetric. But this doesn't solve the entire story. So here is what you will see and what it expands to in Quantum Odyssey. And trust me, even I got so lost with how to arrange these circuits. So even I got lost on how to rearrange these circuits. We will do our live demo. So okay. Okay, actually there is here is the minor update. So now the fancy names has been retired in favor of the plain sounding names. So instead of calling Descent, it's now just called Campaign. Play Ranked is now just called Community. Actually, Play Ranked is actually put as a sub menu. We have Sandbox rather than Forge. Resonance is now called Settings, so Campaign. That is the story mode or Descent. So this is what we have so far. The node which I had like the trouble with is called Boolean Cascade. We will revisit the Boolean logic. So the Boolean logic over there, this is the diagram of the XOR gate and the various permutations of that. This is the XOR gate with 0 as the 0th qubit as the output. This one has the first qubit as the output. Then the last one has the second qubit as the output. This diagram is the custom gate, which the qubit 1 and qubit 2, these two, this is where the concern comes from. So namely, qubit 1 and qubit 2, these are the input, yet this master is the output. Notice that master 2 suggests that the master qubit, the mystery gate, is placed on the second slot. This is a demonstration of how to reverse the XOR gate because it is its own inverse. This is the expanded implementation, and this is the custom gate. We will see similar structures with AND, OR, and XOR, and NAND. We will revisit Boolean Cascade again and see why this is a difficult challenge. So in this case, we are starting with 1 0 0, and we want to bring it to 1 0 1. How can we do that? So an XOR on the second and first qubit would suffice. But here is where the issue comes from. We switch the first and the ground input, the role of these two. This is what happens. We now have the diagram on the middle diagram. So we have this XOR 2 0 1. So this is where the issue came from. Now we switch back. Now we put the input and the output switch together. Okay, this is where confusion comes from. This is where the output is. We have to rearrange the two target gates, and this is the diagram when the output is on the second qubit. So this over there is over XOR second. The answer over there would be an XOR with the second and the first qubit as the input and the ground qubit as the output. Then this is it again. This time we start with 1 1 0. So 1 1. We want to switch the ground qubit on the basis of the first and the second. This one can be done with an AND. This is the output. Drag my masters. This is where the output is used as input for something else. So you're only allowed to use one of these 4 classical gates. So here, you want to switch the 0 into 1. Okay, so this time you can use an XOR. Finally, with a 0 1 1, we use an AND or an XOR, an OR, but not an XOR, an OR. So an AND on the second and the first, targeting the ground, but to work. Okay, now we see how the target gates are rearranged. So the target gates preset, we fill the target gates from the left to the right as much as possible, as long as there are slots. You cannot place it on a row if the gate does not fit this configuration. We're also allowed to actually cheat our way to place it on the very top, but that's not how we intend. This is not how the puzzle is intended. So we assume that the right target gate, the right target component, is the output. The left target output is the other input. We now force truths out of falsehoods. So we start with 0 0 0, and we are only allowed to use the 2 input classical gates. Here, The first one, if you want to promote it to 1, you have to perform a NAND. So NAND. Okay, now we have 0, 1, 0, 0, 1. Okay, we need to perform a NAND again on the first two, but this time the output is 0, 1, 1. Okay, finally we need to perform an AND on the ground and the first, so an AND. But okay, this is one input, this is the other input, and then this second mask, the second target, which is preset, will be the output. Here is a brilliant solution. I'm already gaining knowledge. I should be able to get the bracket 10. This one requires never a straight path from the truth. Okay, this one is actually pretty straightforward. That the only thing that's tricky is there's an extra X gate on the end. So overall, there is a degree of redundancy. This is nothing more than a 4-qubit problem. Namely, you want to switch the lower 4 qubits to 1. We know this drill. NAND, we have another NAND, and we have another AND. Okay, we can perform one more AND, so this time we can perform an AND on the first and second qubits, so an AND there. Okay, but now the masters are filled from the leftmost open slot first. So this is how the AND is being structured. We can also place the gate on the very last. This master is an output, this will be an input. Because the master that's placed preset, the right is the right one there. It has to be moved. We now have a depth 4 solution. So we finish this. We are still on bracket 5, but this is only because it's a demonstration, a walkthrough. Our next live stream will focus on the quantum phenomena. We will focus on the other branch, on the Independence Day live stream. This red path over there will be ongoing, so expect one red path recorded at the end of each of these live streams. So here is the update I have. So let's perform a review. So item 1. The first concern is how multi-qubit gates are represented. So you have seen custom gates, used when the gate is outside of the game's standard set, and you want the gate to take up only one row in the puzzle. This has been demonstrated in the introductory main nodes for different types of 2-input classical gates that are to be demonstrated. This is a standard set, so these are in order. We have the I gate, don't forget about that, the X gate, the Z gate, the H gate, the C gate, which is technically an operator, not a tensor product, the S gate, the Y gate, the SX gate or root X, the T gate, and the HC gate, which this one is non-classical. Which is not in the unitary group. So the HC is not unitary. These are the custom gates you have saw in some of the nodes. This H gate lookalike is called the RT gate. The RT gate is just a RY gate followed by an X gate. This is an RX gate, RX of a quarter turn, RX gate, and it is equivalent to the SX gate up to a phase shift. This red X is a neg X gate, so it's ZXZ. That gate is a neg Y gate, so neg Y can also be expressed in terms of HYH. This gate looks like an S gate, but it applies to the positive eigenvector, which is the zero state. So this is called the X. So this one can be implemented as XSX. So a similar idea can be used for an anti-controlled gate. This gate is called a swap gate. The swap gate is symmetric, even though it is made out of 3 asymmetric gates and it even appears asymmetric. So it's CX01, CX10, CX01. It's also equal to CX10, CX01, CX10. This diagram we all know is an XOR gate. So XOR with the 2, 1, and then 0 as the output. So how are multi-qubit gates represented? So a multi-qubit gate can simply be implemented by applying single qubit gates in a multi-qubit register just in parallel. For example, we have X tensor Z. So X tensor Z would have this 4x4 matrix. So 1, -1, 1, -1. And the indices can be seen as a bit string now. So you can view it as a single number, or you can view it as a vector itself. Z and X together, now switching the places, the matrix would look different. It will now be 1, 1, then -1, -1. So, and IY would basically look like -I, I, -I, I. So the major one would appear like what it appears like from afar, and the operator on the right is what it looks up close. So up close it looks like a Y, but from afar it looks like an I. Control gates are required to realize entanglement, such as CX, which control is on the first, so, and then the CZ, which is symmetric. We have swap, which is also symmetric. And then we have the Toffoli, which is only symmetric between the controls. So what is the definition of a symmetric gate? So let's explain this more formally. Let U be a 2-qubit gate. For example, U can be X and X in parallel, so which is also equivalent to X1, X0, which X1 itself is X tensor I, and X0 is I tensor X. And then CZ, which in a circuit diagram will look like a symmetric gate. So define the gate to be symmetric if and only if the U of AB is equal to U applied to B then A. So if you switch the roles of the two qubits, it still represents the same gate. And they're even represented, it's in circuit diagrams it's obvious that it is symmetric or not. This is a non-example. X tensor I does not equal to I tensor X. This has already been demonstrated in a previous slide in some way. CX, which does not look symmetric either. This left circuit is C1X0. The right one is C0X1. X against X is nothing more than two separate gates applied in parallel, which can also be expressed in series as well. So it's going to be X1 and then X0. We now deal with the multi-way symmetric gates. For example, we have X, we have Y, we have Z. Like this type of entanglement. Or we have a gate that looks like this. So H, then symmetric. H, then S, and then a swap, which this thing will be reminiscent of the next live stream. So what happens if you swap them together? This is where multi-way symmetric gates come into play. Suppose we have an n-gate qubit, let's call this U, for some n that is a strictly natural number. So remember, n plus is the counting numbers 1, 2, 3, so on. It differs by the other natural number set, which is n, which is 0, 1, 2, 3, which some also call it whole numbers. Whole numbers is also ambiguous. It could also mean integers as well. But it's important especially to distinguish these two. If you make a mistake over these two, then it's an off by one error. I am a computer scientist. I have majored in computer science, and everyone knows how embarrassing this bug is. So let's explain how multi-way symmetric gate is. Suppose we have an n-qubit gate called U for some strict natural number n. define the gate as symmetric if and only if for all permutations, let's call this particular permutation sigma, in, let's call it the set of permutations, the symmetric group on n elements called S of n, we have, let's say, U of the permuted sequence is equal to U, where X is the sequence of the first natural numbers in descending order. For example, let's say sigma of 210 is actually equal to this. So this is by definition sigma of 2, sigma of 1, sigma of 0, which broadcasts it to, let's say, 2, this is an master gate, and the 1, 0 are the target gates, 0 and 1. We will demonstrate that the permutation, the U of sigma of the sequence does not equal to the sequence. So we say that this U is not symmetric. In this case, that U I'm referring to is a 3-qubit 2-input gate. This leads to item 2 called permutations. So informally speaking, a permutation is a way of selecting and arranging a number of elements in order. For example, there are n permutations of a set of n elements. So that means, in more formal language, the cardinality of the symmetric group on n elements is n factorial. And we know like n factorial is. N factorial is just pi from 1 to big pi to n, then k, which expands to 1, 2, 3, then so on, n. There are n pk ways to select k out of n elements, which we call this a partial permutation. For example, we want to select 3 out of 5. 3 of 5. So A, B, C, D, E. You can think about as you have saw that before in the 5th puzzle of the classical cascade, which is the electron I have been in concern of, 3 of 5. So the answer is this. 5 P3 is 5 times 4 times 3. You can actually express this in terms of factorial by performing 5 factorial over 2 factorial, which is by canceling out all the remaining numbers. So npk is by definition equal to n factorial over the remainder factorial. So in the last Boolean Cascade, which I have demonstrated, the 3-qubit NAND and OR gates are partial permutation of the 5 qubits. So partial permutation 3 of 5. And then there are therefore n pk ways to arrange a 3-qubit gate on a 5-qubit register. Here is an actual demonstration. So formally a permutation is a bijective function from a set, let's call this S, to itself. The permutations form a group under composition called the symmetric group. And moreover, each permutation in S of n is equivalent to matrix of only ones and zeros, which each row and column sum to 1. This is called a permutation matrix. This means, in other words, a permutation itself can be expressed as a linear transformation. Moreover, it's easy to invert. It's an orthogonal unitary matrix itself. You have actually already saw that in the form of an x-gate, c-axis, and Toffolies. So, formally, a permutation is a bijective function from a set S to itself. We will have an actual demonstration concerning the classical gate. So here we have S is 0, 1, 2. So it's a 3-qubit system. Ground, first, second. Sigma is a bijective function. So bijective function from S to itself. Let's say the master stays in place, and then the targets. So we switch the targets over there. This is where the implications get into play, where the bug report comes from. The problem is this. U of 2, 0, 1 does not equal to U of 2, 1, 0. So this means the XOR, or in fact like any gate, so any gate like XOR and or 2, 1, 0, 2, 0, 1 does not equal to the XOR gate 2, 1, 0. Even though it appears that in the editor it's question mark, the master of that position, master of that position. This thing actually has a real-life implementation, and it's rather theoretical, but if you have learned how to solve a polynomial, especially a quadratic, you might be tempted to think, how can I solve any cubic, any quartic, any quintic, any polynomial? This leads to a very storied tale, which eventually concluded with Abel and Ruffini, and then Galois. In fact, Sophus Lee's work is built directly on Galois theory, also on unsolvability, but this time on an even more advanced subject, namely whether a differential equation is solvable. But Galois, the original, is to state whether you can solve a polynomial in terms of roots or not, power functions or not. So let's conclude today's session with a sneak peek on one of the most important discoveries in maths. For permutations and polynomials, and that is what Galois is about. Just as how Lie groups are about differential equations, and then it happens that it has to do with continuous symmetries like rotations in 3 space. Galois is for permutations and polynomials, and we have already saw the applications of permutations. You should be familiar with the quadratic formula, namely that given a quadratic ax plus b, ax squared plus bx plus c equal to 0, that means all the terms placed on the left side, and a, b, and c are any complex coefficients which a is non-zero, we can find both solutions of x. And moreover, they only differ by the third component, which is in orange. The splitting field, so field is just a set of numbers that's constructed through the arithmetic operations and are closed. So they do not yield any value that's outside of the field, informally speaking. Splitting field is just the smallest field to contain all the roots of this polynomial. Namely, the splitting field is of the form of Q and then the root discriminant, assuming the root discriminant is surd. The Galois group of a quadratic is this. So Galois group of a quadratic is C2 if irreducible. Otherwise, it is the identity group, which is when you can factor a quadratic. So C2 is actually also equivalent to S2 as well. E is just the trivial group. You likely have not seen this form of the quadratic formula, but you can express the quadratic formula in only like 3 components: the B, the 2A, and the 2C. Like, that's all. And then there's a discriminant over there. The Galois group can be thought of the number of the symmetries of the roots, like how does using these roots change some polynomial in the form of these roots, like that. So you're changing the roles of the various polynomials solutions and the inputs, which the output is now taken as the input. So, and see like if rearranging the inputs change the output. In the case of the classical gates, so that's the XOR, the AND, and the OR, and the NAND. So the Galois group, however, can be seen as equal to C2 as well, because the only symmetry there is the symmetry between 2, 1, 0. So this is question mark master master against master question mark master, while there is an asymmetry between question mark master master and the other question mark master and master. This concludes our session for today, and as always, this is our roadmap for the remaining live stream. So, roadmap. So on Canada Day, which we will schedule this at 6 a.m. Eastern Daylight Time, would be the quantum phenomenon. Finally, we have the Independence Day. Again at 6 a.m. Eastern Daylight Time. We have the adders. Good luck everyone, and peace out. Like and subscribe to my channel. Make this thing grow and make Quantum Odyssey and the International Year of Quantum Technology